for accommodating this recording in progress. Great pleasure to introduce Zachary Lipton, with special thanks to the team for this change of schedule. Zach is Assistant Professor of Operations Research and Machine Learning at the School of Business, Carnegie Mellon University. He has made fundamental contributions to XAI. I will list a few here: the Mythos of Model Interpretability, which is a CACM highly cited paper, a critical review of recurrent neural networks for science learning, and learning to diagnose with LSTM recurrent neural networks. So Zach is also, of course, an accomplished jazz saxophonist. Today he is going to talk about integrating symbolic structure and statistical learning to adapt to distribution shift. Thanks again, Zach. The floor is yours.
Great. Thanks for having me. And thanks again for, a real, for saving my butt here and giving me an opportunity to speak at an hour where I'm apparently able to wake up. I've long had this fantasy about giving talks without slides, and I keep chickening out. So I'm not going to do that exactly here, but I'm going to slowly maybe put my toes in the water and at least have a sort of first part of the talk that's mostly without slides. And then some more specific technical part of the talk, and we'll see how much we can fit in the allotted time. On some concrete work, integrating ideas from causality into this problem of developing models that are sort of robust or generalizable in some sense that sort of transcends the typical IID sense. And in general, I think that I think a huge, just perennial point of confusion, both within the core statistical learning community and when I say that, I mean just maybe the broad machine learning community, not necessarily like statistical learning theorists. I think that if anything, the theorists tend to be more sort of head screwed on about this. But I think both within the sort of core statistical disciplines and in sort of on the periphery and other corners of AI, I think people just tend to be sort of maybe deeply confused about what are statistical versus non-statistical concepts and what we mean when we talk about generalizability. And it's very easy to slip from notions of overfitting that concern the size of the sample versus notions of overfitting that concern the applicability to data from one population versus a bunch of different populations from which you don't necessarily have any sample data, but where you might hope to deploy your model. And I think that maybe oftentimes in this sort of, there are these sort of paradigm struggles between the symbolic approaches and statistical approaches, or often between like sort of the kinds of statistical methods that are secured by sort of like a priori demonstrable mathematical guarantees, and the sorts of statistical approaches that are not, where I think the sort of the non-vanilla approach, the non-just train a bunch of predictive models, see what works approach, often maybe sells itself short by committing to the traditional statistical lens. Like I think that most of what's interesting about the world that gets lost is sort of chopped off when you start framing these IID prediction problems. So I think it's in some ways maybe a mistake of the learning theory community to insist that you needed, pack style guarantees for algorithms where the purpose is to perform well on IID data, because you always have, you could always look at the test set. Why should you rely on this extremely loose guarantee when you could just look and see how well you generalize to data from that very same distribution? And I think it's the same, perhaps, in the symbolic community, that there's an over-reliance on the, or I would say maybe simultaneously, and this is, I'm speaking as an outsider offering some opinions here, but what I see is maybe a simultaneous over-reliance on the statistical framing of what problems to look at, and perhaps an under-reliance on some of the more powerful ideas in statistics that would, I think, render some of the aims of symbolic AI more concrete, including questions about, how does one determine what the appropriate symbols are, or how to recognize them? Or when are these questions even identified? So I think like the theory of identifiability as arises in, say, causal inference is really powerful. So the way I'm gonna structure this talk is like, first, I'll tell you just a little bit more background about the kinds of problems that I work on. And then to prepare for this talk, unfortunately, it undid me because I fell asleep at 4 a.m. and then completely missed my alarm. But I wanted to, I guess, not just give my normal talk, but have something to say to this community. And I'll, freely concede that I'm not maybe the authority on the lines of literature that are addressed mainstream within, to say, or at least that fly typically under the neurosymbolic umbrella. And so I found as a nice intro to the field to read Arthur's a neurosymbolic AI, the third wave review, and used it sort of as an opportunity to, I think it's a sort of great distillation of a set of ideas where I don't necessarily agree with all of them, or I might push back on a lot of them, but it made maybe clear for me what some of the commitments of the neurosymbolic school as, say, practice today are, such that I would even know what I was agreeing or disagreeing with. And so what I'd like to do is, all right, first kind of say a little bit what I do, the next maybe give some kind of like higher level arguments about what I think, the broader kind of like field of symbolic AI is sort of doing versus what I think it should be doing. And obviously this is perhaps presumptuous of me to some extent, but I hope it's taken with a sort of tentative and respectful sort of provocation that it's meant as. And then I'll kind of go deeper into a specific way that I see something that feels in some sense like a kind of symbolic reasoning, and something that is clearly doing deep learning really do integrate together in a natural way. And this is exploiting known causal structure to solve these sorts of broader generalizability type problems. And I'll speak about situations under which it's possible to determine what you should do under distribution shift if you have some set of higher level representation, like at the level of, hey, I've got my inputs and I've got my outputs, and I believe that my, intervention on my targets, can influence my covariates, but not the other way around, or vice versa. An intervention on my, the features could have an effect on the target. So, this is the very coarse, high level language in which you could express something that looks like a set of symbolic commitments. It's discrete, it concerns, it has an associated calculus, the calculus of causal inference. And at the same time, it fits together in the sense that the calculus doesn't tell you how to estimate the functions. You still use deep learning or whatever you want. And maybe among the arguments I'll make somewhere along the line is that I think maybe there's too much of a, in my view, and I could be totally wrong on this, and I'm totally willing to be proven wrong by history, but I think maybe in my view, there's too much of an emphasis on the symbols living in the deep neural networks. We're thinking about neural networks as something more like cartilage. Like the job of cartilage and bones need to work together, but it doesn't mean we need to represent cartilage as bones and bones as cartilage. It means we need to connect them to each other, or bones and ligaments or something like this. So I would think of, I'll present maybe some kind of view for one path that maybe is, and Arthur might disagree with me wildly and say it's one of somewhere in this taxonomy, but I think it lies somewhere outside of what's exactly given this taxonomy of, I believe it's not even Arthur's taxonomy, but from Henry Kaut's paper in 2020 of categories of neurosymbolic integration. Okay, so without further ado, okay, so what I do is I run a lab. We call ourselves, in a kind of tongue-in-cheek sense, the Approximately Correct Machine Intelligence Lab. I started adopting this term in the context of running a blog that I guess as I have had more students and spent more time writing papers and have more hours of meetings, I've become less of a blogger and more of a, I guess, a traditional academic. But when I was in PhD, at some point, I didn't have many papers, but I was a more prolific blogger. And I started this blog called the Approximately Correct blog. And then adopted as a name for the lab. And the main reason why is because there's the obvious play on learning theory, like probably approximately correct theory. And we certainly do some statistical foundations work, although it's maybe not my like center of gravity, but I do have a couple very strong theory students. But for me, the bigger meaning is, I think, the second one, the hidden one, which is the ways in which machine learning is always, it's almost always a cartoon. So the question is just what parts are how cartoonish, but what we draw is we draw a cartoon of some problem that we actually want to solve. And we leave out all sorts of important things. So for example, we want to make a decision about how to do something in a changing world. And what we do instead is we say, let's assume the world's not changing and solve a prediction problem. And the hope is that if you kind of, you know, like hide the dirty laundry and you sort of just sometimes switch in a kind of careless way between saying the word prediction and decision, that nobody will notice. And you could kind of get away with this sort of elision, and that maybe it'll turn out that sometimes the heuristics you use to operationalize predictions to make decisions will turn out to be good business decisions, in which case, and indeed, like it often is the case. There's a reason why people use recommender systems. I imagine there's lots of very large companies that, you know, would lose a lot of money if they abandon some kind of statistical approach to recommender systems altogether. And at the same time, there's something kind of wrong. It's not addressing the problem in full resolution. So we kind of go after all these kinds of gaps between what we see as like the real critical gaps between, and we try to like, our focus is technical, our focus is within the machine learning world, but we look at these things up, you know, what are people trying to estimate? If they're, you know, if the estimates are causal and not conditional, how do we get to them? How do we get to them in the kinds of data regimes that we actually care about? If the goal is to perform well in a environment that might be different in some substantial way, and that's, you know, what we say, why we say we want robust models, why people often claim this is desiderata to motivate interpretable models. We try to break down the problem and think like, what exactly are the identifiability criteria under which, you know, determining what you should be doing at test time is even something that can be deduced from the available information. Chat. Cool. Please post questions. Yeah, interrupt me at any time. I'm interruptible. So, you know, for us, this includes questions about robustness on the distribution shift. It includes questions about causality. It also includes questions about sort of societal desiderata associated with machine learning, including questions about, you know, say, discrimination in decisions that are made in a sort of data-driven fashion. So, so some thoughts on the sort of neurosymbolic framing. So at the top, I want to sort of, you know, I think Arthur does this great job of calling out the highest level impulse, or maybe the most central impulse here is, as I understand it, a desire to integrate reasoning and learning. And, you know, I think the appeal makes sense, and that reasoning, it seems like, or at least certain point now I think I would sort of at the very top, I would adopt that you know, these are suitcase words, I think, in that like the whole framing here, what constitutes reasoning, or what are, you know, what constitutes a sort of a calculus over symbols such that it should be applied to any data. is sort of, I think, left as often a fairly open-ended area, which makes, it's hard to pin down what constitutes a symbol or what actually, like, for example, I think you see the sort of nature of like first order logic as claimed as a system of symbolic reasoning, but then also you see the nodes inside decision trees claim to be symbols within symbolic AI. And I think there's a danger to this degree of lumping, because there's a fundamental difference between a symbol that participates in an expression in first order logic that is actually, some claim about some real world entities that are represented by these symbols, and the nodes in a decision tree, which are not actually learned in any way such that any sort of system of like generally applicable, universally holding rules, such as like the rules of deductive inference or of causal inference, applies on that set of symbols. And I think so I guess this brings us to the question of like, what constitutes symbols? And as I see it in the literature, it seems that there's sort of maybe two sides to the symbolic commitment. One side is maybe more about form factor, and it's this question of, are they discrete? Do they take the form of, say, propositions or assertions or categories, versus, are they continuous valued or vector valued? And this, I think, is the framing, and I'd argue maybe to some extent the baggage of a certain lineage of literature. And I'm maybe not the primary expert, but I'm maybe more expert than the typical random person at an ML conference. I've done a little bit of archaeology, but I think to some extent it owes out of the legacy of the Fodor and PDP sort of back and forth, that maybe puts all this emphasis on the presence of discrete versus continuous structures that I think might be somewhat misplaced. I think the other big part that is maybe not talked about as much as it should be, but again, this is coming from an outsider, is the applicable rules of composition. So what constitutes sort of the relevant sorts of calculus is that, does just being the nodes along the pathway toward the construction of a decision tree make a node a symbol? And I would argue no, in that the symbol is sort of has, I think, functionally the same role as just any intermediate node in a neural network, and that perhaps this maybe focus on translating neural networks into logical forms or expressing logical expressions within as neural network architectures is maybe missing, I think, an important point, that what makes symbols powerful is not just that they're discrete, but it's that something like the rules of mathematics or the rules of logical inference or the manipulations of the do calculus could be applied on top of them sort of profitably for producing new facts that actually, or at least, in ways that give you some kind of guidance for how to behave in the world, perhaps even in situations that you haven't been in before. And I would argue that at a high level, I think this over focus on form factor is a general sort of pox of explainability research. And when I say explainability research, I'm maybe now coming all the way back to the main branch, like NeurIPS ICML sort of explain the black box neural network approach. But I think in general, there's been a sort of tendency of folks to think too much about what should an explanation look like? How does it arrive? Is it words? Is it a heat map? Is it something else? And less about the semantics, like what actually is it telling you? And so I think there's a danger of sort of saying a cosmetic sort of, sort of overthinking too much about how do I produce things that look discrete, because I think of symbols as discrete, when what really mattered all along was that this was the sort of right representation such that you could bring a kind of like universal you could bring one of these motors to bear on it. As these motors, I mean, with the rules of mathematics. And I would note that, calculus itself, right? Like at least what most people mean by calculus is a calculus that applies on continuous representations. So the point here is that even though neural networks are differentiable, neural networks do not do calculus. They do not discover calculus, and they do not apply calculus on representations of the things that they learn. But if they did, I would argue they would be doing something symbolic. And maybe there's something discrete, maybe the actual expression of the functions are discrete. the sort of expression of the compute graph or something of what you should be, what operations you should be running, but the actual sort of underlying entities that are representing the world could be continuous. I think there's also a question of, I think something that gets glossed over is, what is the basis on which you conclude that there is something in the world that should be represented by a symbol? And I think that there's a lot of talk about grounding, but I think what's gotten lost in something of the symbolic versus connectionist approach is that maybe one thing that neither the symbolists nor connectionists were good at traditionally was statistics. And when I say good at statistics, I don't mean they couldn't calculate a confidence interval or something like that. But what I mean is that some of the more profound ideas of, say, identification are maybe sort of missing in the first place, in that and maybe the sorts of things that are missing I see missing when people talk in the deep learning community, but maybe I think I also see them when I see sort of some of these passionate arguments for the symbolic AI, a question of what are actually the statistical principles on which you identify and conceive of and mark a new symbol. Like how does such a binding actually arise? And I think it's something that is almost always sort of glossed over in a kind of hand-wavy sort of way. And so what I want to make an argument for in part, and I'll give some toy works that I think are in this spirit, but maybe not like telling the whole picture, is to be bringing to bear some, like on one hand, I think we need to be less focused on statistical prediction in this sort of narrow IID sense, but I think we need to be more focused on statistical principles, even if it's at the level of a toy model. The sense of when, if ever, can we actually seize a set of symbols? Do we actually, what is actually required for us to determine what the right symbols are? And there's this sort of dance here, which is that if you have a certain calculus, then you can come up with, you have a question of developing the right set of symbols to apply the calculus profitably, versus if you have committed to your set of symbols and there's a question of what's the right set of calculus in order to do something useful with this representation of the data. Right. So I'm going to go into just a little bit these specific works now. I'll give an example, and hopefully just the high level kind of make some of my point of one way that you can integrate a sort of symbolic approach is that, so let's just think generally about the problem of adapting under distribution shift. And I think this is something that's maybe lost on people that don't work on this problem from a statistical perspective, is that, in standard machine learning problem, you're told God showers data out of the sky today, and God will continue to shower data out of the sky tomorrow. And we can collect some data today, randomly partition it, and it's as though we had data from tomorrow. So we could basically train on one side, evaluate on the other, and this will tell us how we'll do at test time. And reality is that, we're deploying the model in a changing world. So you might think, well, let's just come up with a robust model. And the problem is this is in general impossible. If you don't tell me how the world's going to change, I can't answer the question. I can't generalize. Even, we focus on these complex machine learning problems, but you could just take yourself back to the most simplest statistical prediction problems. Estimate the prevalence of a disease, estimate the mean of a population. You can't do it if you don't know, like in general, collecting data from one population P doesn't give you the ability to estimate any parameter on some other population Q. So you need some kind of model for how the world changes, right? Creating a single robust classifier is impossible. I can always just contrive a distribution. It doesn't even have to be contrived in the sense of like a really tortured example. I can come up with two really plausible examples, both of which describe things that would happen in the real world. And just having data is fundamentally can't tell you what to do. It doesn't matter if you're symbolic. It doesn't matter if you're adopting a neural network. So it's impossible to come up with a robust classifier. So what can you do? So here's like our first foray into this was addressing the problem of label shift. So label shift, basically you make a simple assumption. You say, hey, I have some data X I have some target that I'm trying to predict, or I should say some label that I'm trying to predict y, my assumption is that what happens, the way data is generated in my world, is that the y's are first fixed, and then an x is generated conditioned on a y. So one way of motivating this would be, hey, the relative number of cats versus dogs might change, but what a cat looks like or what a dog looks like doesn't change. And so the underlying prevalence of the categories could change, but the manifestations, the probability of x given y, the class conditional distributions, they can change. So now I've created these two symbols. One is sort of like something broadly, all of like images, and the other is like, categories. And I've said there's this model that relates them. It's a discrete structure. It's a symbolic structure. But what it tells me, what I've said nothing about is what is the form of the function f of x given y or f of y given x. And so the point here is not to use a neural network in any sort of way to sort of discover the underlying categories by looking at the neurons, but instead saying, hey, I have this high level causal structure at the level of how the inputs, which are images, relate to the outputs. How can I bring this to bear to tell me how to answer this out of domain problem, right? So to skip ahead, basically, it turns out that what you can do is you can come up with any predictor, train a neural network. Just the fact that you can in general do good prediction is enough. You train your predictor on your source data, you come up with a classifier. And then what we develop is a model called Blackbox shift estimation. It sort of says, well, when can a predictor that's good on the source domain answer the question, what is given labeled data from the source domain and unlabeled target from the unlabeled data from the target domain, tell me what is the class distribution on the target data? And it turns out there's a set of if we've assumed this causal structure and our classifier satisfies some basic probability, some basic properties, then it allows us to identify this, the target label distribution, and then in turn, on the fly, update our classifier by sort of post-correcting the probabilities to reflect for this change in the likelihood ratios. So we start off with a situation where we have a very simple, at a very abstract level, characterization of our data that sort of has a symbolic structure. It encodes some kind of knowledge about what's allowed to change versus isn't allowed to change in the world. But then we compose this together with neural networks. And the point here is that this is now like sort of solve this end-to-end problem in a way that doesn't require that the neural network inside is really bumping around, discrete symbols, doesn't care. The point is the neural network is allowed to be the connective tissue. It's just the function approximator. And the symbolic structure is given by the causal structure. And the synthesis of these two is allowing us to answer out-of-domain questions. The fact that we're able to learn good function approximators, and the fact that we have this system of symbol manipulation that allows us to express assumptions about what is stable and what is unstable in the world and derive, sort of optimal parameter estimates for performing well in the target distribution, or at least determine when it's identifiable at all. So in short, we have this approach and it works precisely in this fashion. So we're able to get even basically a mild set of assumptions on your classifier under which it's sufficient for producing a consistent estimate. We're able to get nice error bounds. We're able to show that it works empirically. And so here's I think just one step further into this line of work is to say, well, then when can we discover a new class? In some sense, there's something I think that feels symbolic about this. I've seen cats and dogs before. How do I look out at the world and say, there's not just cats and dogs now, there's cats and dogs and rabbits. How do I estimate? And so this is from a new paper. I think it's posted to archive today or tomorrow. It just got a spotlight talk at NeRIPS with my student Saurabh Garg, where basically we look at this problem, and the normal symbolic neural framing, I think both sides sort of miss this identification question of when in the first place, when under what circumstances at all can I conclude that there is a new class? And it turns out that you can come up with something much like the label shift assumptions, and it gives you statistical principles for determining when is it, because if we assume that the class conditional distribution of every class is fixed, the only thing that changes is the relative prevalence of the classes, and additionally there can be a new class, then we're able to determine under what circumstances we're able to estimate basically the fraction of the new examples that belong to the new class, and then to turn that estimate in turn into an updated classifier that can recognize not only the previously seen classes, but also elements of the new class. So this is a case where the role of the symbolic structure is to express our sort of like a sort of more abstract kind of set of assumptions about how the world's allowed to change or not. And it turns out that if you don't do that, no amount of data is going to help you. I think one thing that is like a danger is that there's a tendency to say, oh, if we have symbols, we solve causal inference. The problems of causal inference are fundamental. And they're fundamental in the sense that, you know, a non-identification result is a non-identification result. And what that means is that causal inference isn't just a problem that you solve, it's also a problem that sometimes tells you it cannot be solved. And it cannot be solved regardless of whether you, you know, whatever goes inside your box, whether it's symbols or you know, continuous activations connected to each other. So these are sort of like two sides of the coin. One is, yeah, and I won't have time to continue talking now, but if you're interested, this work is called Mixture Proportion Estimation in PU Learning, a Modern Approach. We have a few papers, but I guess the main one is detecting and correcting for label shift with Blackbox predictors. And I didn't get to talk about our work on counterfactually augmented data, but I think has something of a similar spirit of not tampering with a black box, but rather thinking of how do we dance around it and do our sort of synthesis at that level of using a sort of symbolic structure for expressing these higher level commitments about how the world's allowed to change, and a black box to actually fit functions without worrying about what's inside.
Right. Thank you so much, Zach. There were some discussions in the chat there on symbols versus neurons. The community meeting starts soon, so we don't have a lot of time. I just wanted to comment that, yeah, you're indeed looking at some key new aspects that are very relevant, such as new classes and counterfactuals, causality, and enhancing such deep network models. So I find that very important. In terms of neurosymbolic computing specifically, I see translations from one language to another as a way of trying to organize the field. And as we are probably now at a position where we can move into addressing these broader aspects. And I think it will be indeed high time for identifying the key ingredients, and then of course the techniques that will be used. So that's more of a comment. But thank you so much again. I think the questions were mostly on the symbolic versus sub-symbolic aspects, such as, for instance, well, you could take the approach that if it's happening inside a computer, then it's symbolic, and
right.
I think we are at a point.
And then you could also take the approach that if it's expressible in any kind of circuit, then you can build a neural network that will express it. But right. At that point.
That's right. Yeah.
I guess a little bit like this sort of commitment of when you see operating systems or like programming languages, all of which more or less are the same. Same from not from a standpoint of usability or poetry, but same from a standpoint of expressiveness. But where they differ often is in a really profound way is their choice of metaphors. Right, you have all these concepts don't exist in the real world. There's something, and you need some organizing metaphor, and you wind up torturing some idea to mean much. So example would be like Linux. Everything is a file. Everything is a file. Like we have a connection between our computers. The connection is a file, right? There is this folder has a parent. Well, the location of the parent is a file. Like everything is a file, and that is the dominant organizing metaphor. And it's not that it gives you something that you couldn't express if you had chosen some different way of articulating. You have other languages where it seems like everything is a stream.
Yeah. Or every vector is a symbol, but not every symbol is a vector.
Right. So but at some point, right, it's like what is different? Maybe what's different is primarily like the way you derive intuitions rather than the set of things you can actually articulate.
Great. So thanks again. I think the point about counterfactuals and causality is also very relevant. It would be great to have more on that, but we'll have to organize that for another time to go deeper into some of the technical aspects. Thanks again, Zach. We now have chance for a 5-minute break before the community meeting starts. And just want to thank the organizers again for allowing this to happen. I'm very pleased, and I'm sure everybody else is very pleased that we had a chance to have the talk as part of this event.
Thank you so much, Arthur. And
thank you. And
sorry again for
no, the time differences
alarm
are
failure.
quite difficult to make sense. And we had a session earlier today with Tokyo and Seattle. So it's amazing what this is allowing. But I hope that next year we can have it face to face. Yeah, thank you also. See you at the community meeting when we'll be discussing the next event. So looking forward to that. Thanks, Zach.
All right, take care.